Hi, everyone. Today we're going to talk about collisions in our Chapter 9 over linear momentum and center of mass. So first we have these two cars. Okay, we're going to talk about the graphs and equations for collisions. So these two cars, blue and white car, looks like they crashed together, but they are not coupling. This actually looks mid-crash. You can see there the wheels are actually coming a little bit off the ground there, so that's probably mid-crash. These don't seem to be coupling, though. This is also a test dummy course. You can see those are not real people. You also have the testing logo on the cars. So this is not some real-life dangerous act we're analyzing. These two cars come in for a collision, collide head-on, make a force versus time graph for the collision of these cars. So let's get a graph ready. Let's see. We've got force on the y-axis in newtons. We've got time in seconds. So we've got the blue car and the yellow car coming in for an impact. So these will look like a big peak, but they will mirror each other. Oh, that's not a great mirror. Let's see. I mean, it's not, the blue is not even really great to begin with, but so there we have two peaks, right? They're going to experience an equal force, but in opposite directions, right? Equal but opposite. We've got a Newton's third law pair here in collisions. Right? So you've got blue car there, got your yellow car here. So they're going to have equal but opposite interaction, right, in a collision. That's how collisions work. Now, frozen a little bit. Let's see, is it frozen on here? Yeah, it's frozen on there. Let's see, there we go. Okay, working now. So we've got a force versus time graph for the collision of those cars. Equal but opposite, trying to nail down the point that this is a Newton's third law interaction. Now let's write down an equation to analyze this collision. Okay, so first, let's show that this is a, we have equal impulse, right? You've got the impulse on 1 equals the negative impulse on 2, right? You can see there that, you know, if my art were perfect, then the area under each curve would be about equal, but they would be opposite in opposite in signs, right? So if we add I2 to the other side, you've got I1 plus I2 equals 0. We can also say that the impulse interaction can also be defined as the change in momentum to an object or to a system. So instead of I1 and I2, we can say that is delta P on object 1 plus delta P on object 2. That will also equal 0. Okay. Then we can split this up. Delta P, okay, is P final minus P naught. So we'll take the P final of 1 minus P naught of 1 plus P final of 2 minus P naught of 2, and that all equals 0, right? Now we can actually add these around a little bit. If you notice here, we can take the initials, right? The initials are negative. You can see there, initial 1 and initial 2. If we add those to the other side, you could get the concept that the final momentum of 1 plus the final momentum of 2 equals the the initial momentum of 1 plus the initial momentum of 2, which gives way to the idea that the final momentum will equal the initial momentum. Which is the idea of conservation of momentum, right? So we can see that expressed in this collision, right? So for collisions, in general, momentum is conserved. Right? Now, we also want to look at this as this crash is shown, right? Is it elastic, inelastic, or perfectly inelastic? And we'll talk about those on the next slide. But here we see that the cars seem to have separated a little bit, right? They do not seem to have stuck together, so that can be perfectly inelastic. But the cars realistically are going to come to a stop, right? They are not bumper cars where they will just continue off in their own directions. So that won't be perfectly inelastic, also won't be elastic. So this is an inelastic collision. Okay? We'll talk about why now. Okay, so this usually in class, all this information pops up as we discuss it, but I can't really do that on these videos easily. So in an isolated system, this is important, right? In an isolated system, that means that there is no work or impulse being done to add energy, add momentum, or take away energy or take away momentum. Okay, isolated system. We're going to look at these three ideas along here. Okay, we've got first, is momentum conserved? Is kinetic energy conserved? Then what is some real life example? So momentum being conserved, right? In all of these, yes, elastic, inelastic, and perfectly inelastic, the momentum is going to be conserved. Because this is an isolated system, in a collision, there is conservation of momentum. Okay. Now, before we talk about kinetic energy being conserved, let's talk about what the definition is of all of these collisions. Okay, so for perfectly inelastic collisions, that means that there is no energy loss due to heat, potential energy, any other conservative energies. There's no kinetic energy loss at all. But in an elastic collision, the definition is that it is momentum is conserved and kinetic energy is also conserved. Now that does not mean velocity is conserved. Velocity is not conserved. The idea that velocity is conserved is completely misunderstood. Velocity is not kinetic energy. Kinetic energy is 1/2 mv squared. Just because the kinetic energy is conserved does not mean the velocity is conserved. But kinetic energy will be conserved. The kinetic energy before the collision will be equal to the kinetic energy after the collision. Then for inelastic and perfectly inelastic, we have a no. Kinetic energy is not conserved in these. So let's talk about perfectly inelastic first. Perfectly inelastic is when you have maximum kinetic energy loss, and this is when your objects are going to stick together, as you can see down here, right? These objects stick together after they collide, and they either continue moving as a couple or they come to a stop afterwards. So just because there's maximum kinetic energy loss doesn't mean that that has to be zero, right? But their relative velocity would ideally be zero. So let's talk about the coefficient of restitution. This is a quick side note, not something we actually use in any of our problem solving stuff, but a really cool talking point. Okay, so you've got let me write it out, coefficient of restitution. Restitution. And this is shown by E. Okay, and E equals a ratio. Okay, this is the ratio of your relative velocity after the collision divided by the relative velocity before the collision. Now this relativity is important, right? But in a perfectly inelastic collision, this coefficient of restitution should be zero or be approaching zero, right? It is the idea that the relative velocity after the collision is so small it would be negligible relative to the velocity before the collision. Right? So for example, a very bouncy ball, right, would have a very high coefficient of restitution because the relative velocity after the collision would be very close to the relative velocity before the collision. Let's say you have a V naught of 5 meters per second, right? If you have a V final of 4.99 meters per second because your ball is very bouncy, then your coefficient of restitution would be approaching the maximum value of 1. Right? A ball that does not bounce very well, okay, let's say it has a low velocity, a low final velocity. Let's say it goes down to 0.25 meters per second. That means that your E would not be high. You would have the value 0.25 divided by 5, which is a really low number, right? So this is going to approach a lower and lower number until that eventually approaches 0. Now 0.25 obviously doesn't approach 0, but as that relative final velocity gets lower and lower, your coefficient of restitution approaches 0. Now, inelastic collisions, these are collisions that you're going to interact with most, and we're going to talk about that in a second. This is a collision in which kinetic energy is not conserved due to some kind of internal friction, whether it is literal friction, whether there is heat exchange, whether there is the compromise of the internal structure. No matter what's going on, usually there's just some internal loss of energy in an elastic collision. Okay. Now, an example of each. Okay, an example of an elastic energy is molecules colliding in the air. Right, the air doesn't eventually collide itself and have too many collisions to the point that it just gets kind of tired, starts moving slower and slower and slower. That's not quite how air works, right? So molecules colliding. They conserve their kinetic energy. They also conserve their momentum. So those are elastic collisions. Also, if you were to find a perfect bouncy ball, which I don't know that you can find, but you might find something very close to perfect, where you can drop a bouncy ball, it bounces off the floor, preferably a hard surface like tile or concrete, right? Bounces off the floor and will return right to where it was dropped, right? You don't have to move your hand at all. You drop it and it comes right back to you, okay? That would be a perfect bouncy ball. Very difficult to find, but really cool if you could. Next, inelastic collisions. These are going to be most of the collisions that you encounter with energy loss. Okay, there is most collisions have some kind of energy loss, whether it's due to sound, heat, or some internal friction, or for example, a ball deforms its surface and then springs back. That deformation can actually sometimes cause a transfer of energy as well. There's also no sticking involved in inelastic collisions. Okay, that is reserved for perfectly inelastic collisions. They will stick together. All right, now let's look at the concepts. Collision concepts and equations. So we've got useful equations for elastic, perfectly inelastic, and inelastic collisions. So in elastic collisions, we have the conservation of momentum, right? Summation of P initial equals the summation of P final. But what we also have is the summation of kinetic energy initial will equal the summation of kinetic energy in the final state also. So you've got two equations for elastic. But for perfectly inelastic and inelastic, you only have conservation of momentum to deal with. They don't have the conservation of kinetic energy. Now, I also want to note that the conservation of kinetic energy is not the conservation of energy, right? Just because the fact that the summation of kinetic energies, just because those are equal, or sometimes those are not equal, right? For the case of inelastic or perfectly inelastic collisions, that doesn't necessarily mean that energy is not conserved, okay? For example, if the initial kinetic energy is transferred into gravitational potential energy or spring potential energy, that means that kinetic energy would not be conserved, right? That means that the kinetic energy initial is no longer the same value in the final state, right? That means that you started with some energy, and now that kinetic energy is zero because it came to stop. It came to rest at some height, or it came to rest as it compressed a spring. That means that kinetic energy is not conserved, but that doesn't mean that energy wouldn't be conserved. Energy can still be conserved even if kinetic energy is not. So now from a momentum point of view, is anything really different in these cases? The short answer is no. Okay? If you look at momentum, you're going to have conservation of momentum in all three of these cases. Okay? The only difference is going to be that in perfectly inelastic, you have two objects colliding together. So instead of having two separate momentums, you will usually have one final momentum where you have to combine both masses. We'll do that in the next video. But where momentum is conserved, the collisions are basically all going to be the same. Okay? That's going to wrap up our video on collisions, and we will move on to forensic analysis using ballistics in our next video.